is worthwhile. And I still do not need any techniques that we have not talked about. I don't need a table of prime numbers. I don't need any one of those constructs that we have not talked about. So here we have a little digression of how do we optimize this algorithm. And in order to optimize the algorithm, we'll just write it down here. TAG has a hunch that we can optimize this algorithm so that if n is a prime number, we only have to test up to about the square root of n to conclude the number n is prime. Okay? Does everybody understand what my hunch is? My gut feeling? Okay. So the first step to utilize this gut feeling is to formalize the gut feeling and say, but what exactly am I talking about here? I will not use all the math notations, but I will get into enough of the math notations just so that it is not ambiguous. Okay. TAG claims that given two integers, a greater than 1, b greater than 1, define the product as n. So we say that n equals to a times b. Okay? In other words, give me any two integers. Okay? Give me an integer a that is greater than 1, which means it has to be at least 2. Give me a b, which is also at least 2. I will define n to be the product of a times b, just by definition. This n has nothing to do with the n, in the algorithm. This is just, an n that I choose to use in the proof. Okay, TAG says that a times a has to be less than or equal to n, or b times b has to be less than or equal to n. That's my claim. Okay, anytime you give me an integer that is greater than 1 and another integer that is greater than 1, these two can be the same too. I will say that a times a is less than or equal to n, or b times b is less than or equal to n. That's my claim. Does it seem to make sense to you? No? Well, let's try some real numbers. Let's try 4 and 5. Okay? 4 and 5, that means n equals to 20. 4 times 4 is less than or equal to 20. I'm done. Because this is a disjunction, I only need one side to be true. Does anyone want to pick a different pair of numbers as an example? 5 and 7, okay? A is 5, B is 7. N, by definition, is 35. 5 times 7 is 35. 5 times 5 is less than or equal to 35. I'm done. Okay? Can anyone come up with a counterexample to show that this is not right? If I say that if you guys can come up with a counterexample, you can have my Miata. Okay? Can anyone come up with a counterexample? 0. I know a Miata is not an incentive to most people, but
up there.
Huh?
Up there.
Well, first of all, you have to be able to fit in the car first.
What if one of your numbers is negative?
Well, it cannot be negative because it has to be greater than 1.
What if you put 7 times 5?
7 times 5?
Yeah,
Let's
A,
try it.
same.
We have 7 here, we have 5 here. Okay, A is 7, B is 5. So n will still end up as 35, right? 7 times 7 is less than 35 is false. But this is a disjunction. I have a second chance to make it true. 5 times 5 is 25. 25 is less than or equal to 35. Okay? So intuitively, it seems to make sense. Okay? If a number is a composite, at least one of the factors will be less than the square root or less than or equal to the square root of the number. Let's pick a case where A and B are exactly the same, because that's your best shot at finding a counterexample. A is 7, B is 7. if A is 7, B is 7, N is 49, 7 squared. 7 times 7 is 49. 49 is less than or equal to 49. It's true. I'm done. So it seems to make sense. It seems like it is impossible to find a counterexample. But can you prove that it does not? No counterexample exists in this case. Can you prove that? Okay. Why do we have to prove it? Isn't that gut feeling good enough? I mean, no, you guys don't think so? I mean, we're just dealing with prime numbers here. I mean,
yeah, I hate to break to you that there are cases where you can't prove things.
There are cases where you cannot prove things in mathematics. Yes, that is true. In fact, there are certain, not algorithms, but there are certain programs or certain state there are certain machines that you cannot determine whether they will even terminate given an input. That's Turing's theorem. But in this case, it's easy. I can actually prove it. But the part that I want to emphasize is why do I want to prove it when I cannot find a counterexample? So in order to do that, in order to show you the importance of that, we have to kind of travel back in time, back to my graduate school days. Here that goes again, back in the good old days, right? Well, trust me, I don't have nearly as many good stories to tell as some of your other professors. Okay. So back in graduate school, I was working on my dissertation, and my dissertation was based on a particular theorem. Okay, a theorem is basically a mathematical statement saying that blah 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 has to be true. Okay, that's basically a mathematical theorem. So my dissertation was based on that theorem, and at first it seems to make a lot of sense. This has to be true. Intuitively speaking, it makes sense. But at some point, I was kind of getting a little anxious, okay, because I was feeling that maybe it's not true all the time. I asked my advisor and asked him, do we have a proof of this, theorem? Because I would like to see it just to confirm, to convince myself before I go any further in my dissertation that this theorem was true to begin with. My advisor told me, well, this theorem was proved in a master's thesis that was done before my dissertation. So it has to be done, has to be true. And I asked him for a copy of the master's thesis. I reviewed the master's thesis. The only proof, quote-unquote proof, of this theorem was blah, 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 blah. Obviously, this has to be true, okay? Without any actual rigorous step-by-step proof, it was a conclusion. It was a jump of conclusion to obviously this has to be true. So that was no mathematical proof at all. I was bugged, really, really bugged. And my advisor said, don't worry about it. This is true. We have used it already, so we know it is true. And I did not feel, comfortable with that. I spent a whole week to find a counterexample, and I found one. So I went back to my advisor with the counterexample, showed him, okay, in this particular specific case, the theorem would not be right. That statement in the theorem would be false. It is not true anymore. My advisor only said one word. Oh, that was it. Okay? And to me, it was not a bad thing, because I was only getting started with my dissertation based on that theorem, so I can just change it, to use another theorem or, to understand exactly what it is, the actual property of the problem. I went back to the computer lab, the AI lab. This is an artificial intelligence, lab, and I told this to my one of my lab mates. He was about 2 years into his master's thesis, which is about 2/3 done already. I told him about this, and he went ballistic because his own thesis was also based on the same theorem, and he's already into it for 2 years. So he just went ballistic. Yeah. But then you guys will say, yeah, a few graduate students have to spend a few more years in the graduate school. What is the big deal? But what if what if a theorem, quote unquote theorem, was proven by obviously, and it was used in the algorithm used in a nuclear plant? Okay, since we were talking about nuclear plants a little bit earlier, and that really kind of shows you that sometimes a gut feeling that this has to be true is not good enough. Okay, it is always better to be able to prove it with mathematics. Then it is better. Okay, it makes you feel better as a programmer, and it makes your clients feel better too. All right, so let's go back to this particular case and say, how can we prove it? I mean, how can we prove that given the numbers satisfy these particular requirements, this has to be always true. This has to be true all the time. How can we prove something like that? How many of you have been in classes in mathematics where you have to prove something? Okay, algebra, calculus.
Geometry.
Sorry? Geometry. Okay. So in geometry, do you guys prove by contradiction?
Yeah.
There's proof by contradiction? Okay, so we can do the same thing here, proof by contradiction. Let me just explain a little bit about proof by contradiction first before we take a break, because this will take a little bit of time, so we want to break, we want to do this after the break. Okay, let's just forget about this algorithm and proofs and stuff like that. Let's think about socks in my drawer. Okay, let's just say that I only buy 2 types of socks. Okay, there are only 2 types of socks that I buy, and I mix all the socks in my drawer. Okay, I don't pair them up before I put it into the drawer. I'm kind of messy. So the question is, if I pick 3 socks out of my drawer, am I guaranteed to have 1 pair?
Yes.
Yes.
It's intuitive, right? No?
Depends on how many socks are in the first place.
What if you buy more than one kind?
It's like a risk game. About your side.
What if you buy twice as many, like if you have black socks and white socks, but if you buy twice as many white socks as black socks,
Yeah.
you guaranteed to get more white socks than black.
No, I'm picking. I'm just randomly. It's early in the morning. I'm just reaching into the drawer. I pick like 3 socks out of my drawer. I only want to. I'm asking whether I have 1 pair of socks. I don't care the color. Okay, I just want a single pair. Right?
If you're guaranteed.
Am I guaranteed to have a pair? Right? I cannot know which color it's going to be. That's probabilistic. I don't care. So the question now is, can you prove it? How do you prove that if I draw 3 socks out of my drawer, I only have 2 types of socks that I'm guaranteed to have a pair? There are 2 ways to prove stuff like that. One is you actually do it empirically. Okay, you say you have 1 pair of white socks, 1 pair of black socks. Okay, and you number the socks so that individually each one is identifiable. And then you say, how many ways can I draw socks out of my drawer? Well, it's going to be 4 choose 3, which is 12 ways. And then you prove to me that each and every case, drawing 3 socks out of the drawer, so that would be 4 times 3 times 2, which is 24. So there are 24 possible cases when I only have 2 pairs of socks. And then with each one of the 24 cases, you can say that, see, in this case you have 2 white socks and 1 black sock. See, in this case you have 1 black sock, 2 white socks, and so on and so forth. So individually, you can prove in all 24 cases that I have exactly 1 pair of socks out of the 3. Now, what if I tell you I have 20 dozens of black socks and 6 dozens of white socks? You can still use the same technique, but the number of cases will be a lot more than 24.
You can use X and Y.
You cannot use X and Y, but you can prove by contradiction. Now, proof by contradiction is saying, let's say tech is wrong. Okay, I draw 3 socks out of my drawer, and I do not have a single pair out of the 3 socks. Now, if you have 3 socks and you don't have a single pair, what does that imply? You have 3 different types of socks. But